Hello there. In this video, we're going to continue our discussion of the sum of positive integer powers. So in the last video, just to quickly recap what we talked about, was the sum of the consecutive integers from 1 to n can firstly be expressed in summation notation as the sum from k is equal to 1 to n of k, and that's going to be equal to n times n plus 1 over 2. So we proved this expression by using a very, I guess you could call it a cute trick, by considering the sum from k plus 1 squared minus k squared, and we showed that this is equal to the sum of 2k plus 1. So we're going to approach this problem in a very similar way. Alright, so first off, we're going to consider the sum of consecutive squares this time. So k squared. So this is going to be equal to 1 squared plus 2 squared plus 3 squared plus 4 squared plus all the way up to, say, n squared. So our goal is to pretty much figure out, okay, what is this going to be equal to? Alright, so in order to find that out, let us first look at a identity. So what is k plus 1 cubed minus k cubed equal to? So this is almost like the same exact start as we did in the consecutive integers proof, except we've just increased the power by 1. So k plus 1 cubed is going to be equal to k cubed plus 3k squared plus 3k plus 1 minus k cubed. And that is going to be equal to, so the k cubes are going to eliminate from one another, and that's going to be 3k squared plus 3k plus 1. Alright, so let us sort of summarize what we have in front of us now. So that means the sum from the last video of k is going to be equal to n times n plus 1 over 2. I'll just abbreviate the sum as so. Let's assume that means k is equal to 1 to n. And the sum of k plus 1 cubed minus k cubed is going to be equal to the sum of 3k squared plus 3k plus 1. Alright, so we're going to be working with this, and we're also going to use this in the proof as well. Alright, so let's begin. So the sum of 3k squared plus 3k plus 1 is going to be equal to the sum of k plus 1 cubed minus k cubed. As we saw in the k plus 1 squared minus k squared, this term was a telescoping series. So let's see if we can get that here as well. So let's start with k is equal to 1. So when k is equal to 1, we have 1 plus 1 is going to be 2 cubed minus 1 cubed, and then plus 3 cubed minus 2 cubed, plus 4 cubed minus, so 2 cubed is this going to be 3 cubed, plus all the way down to, and the last term is going to be m plus 1 cubed minus n cubed. The preceding one is going to be n cubed minus m minus 1 cubed, and all the terms before it. Alright, so what cancels here? So that term will cancel out with the next term in the next series. So this term is going to cancel with that term of that series. So if we sort of work backwards here, this term is going to cancel with that term. This term is going to cancel with the term that's in the first set of the next. And 4 cubed is going to cancel with the last term of the next. So everything is still going to cancel out with itself because, again, this is a telescoping series. So the only thing that we're going to be left with in this case is going to be equal to negative 1 cubed plus m plus 1 cubed. And we can just rewrite that as m plus 1 cubed minus 1. So that is the sum of k plus 1 cubed minus k cubed. And this is a very interesting relationship because then you can generalize this to higher powers. So in general, we have the sum of k plus 1 to the n minus k to the n is going to be equal to, and that's from k is equal to 1 to m, that's going to be equal to m, I don't want to mix them up, let that be m and m. So that's m plus 1 to the m minus 1. So that's the general identity that you can prove by mathematical induction. Alright, so let's go back to our main focus. So we already showed that k plus 1 cubed minus k cubed must be equal to 3k squared plus 3k plus 1. So if that is true, then that means the sum across all of these values must also be the same. So that means the sum of 3k squared plus 3k plus 1 must be equal to the sum of k plus 1 cubed minus k cubed, and we've already shown that that's equal to m plus 1 cubed minus 1. So now we're going to work on that equation directly. So let's simplify the right-hand side of this equation before we focus on the left. So we have the sum of 3k squared plus 3k plus 1 must be equal to n cubed plus 3n squared plus 3n plus 1 minus 1. So the ones will cancel here, so then we're just going to be left with the sum of 3k squared plus 3k plus 1 must be equal to n cubed plus 3n squared plus 3n. Now we're going to focus on the left-hand side of this equation now. So now we have 3 sums of k squared plus 3 sums of k plus sum of 1 must be equal to n cubed plus 3n squared plus 3n. So we know what the sum of 1 is, that's just going to be n, and we know what the sum of k is, that's going to be n times n plus 1 divided by 2. And this sum of squares term is actually what we're aiming for. So we know everything else in this expression in terms of n, and we know that our goal is pretty much, there. So we can just solve for it. So let's do some algebraic manipulations before we get to that step. So we have 3 sum of k squared plus 3 divided by 2 n plus 1 plus n must be equal to n cubed plus 3n squared plus 3n. Alright, I'm going to multiply all the sides of this equation by 2 in order to get rid of this denominator of 2, just to make our calculations a little bit more easier. Alright, so once I do that, I'm going to multiply everything by 2, so that's going to give us 6 sums of k squared plus 3n squared plus 3n plus n, so I've just followed that out. And there's supposed to be a 2n here, so 2n plus 2n cubed plus 6n squared plus 6n. Alright, I'm going to combine like terms on the left-hand side. So I have 6 sums of k squared plus 3n squared plus 5n must be equal to 2n cubed plus 6n squared plus 6n. So now I'm going to isolate my equation, so 3n squared from both sides of the equation, and I'm going to move my 5n to the right side of this equation. So then I'm going to have 6 sums of k squareds must be equal to 2n cubed plus 3n squared plus n. So now what do I have here? So I can factor out an n out of the right hand side of this equation. So I have sum of k squared must be equal to n times 2n squared plus 3n plus 1. Factor this polynomial on the right hand side, you can do it by decomposition and grouping. So that can be rewritten as 2n squared plus 2m plus m plus 1. And I can factor by grouping the first 2 and the last 2 terms. So I can factor out a 2n out of the first 2 terms, so that's going to give me m plus 1. I can factor out a 1 out of the second set, that's going to also give me m plus 1. So I notice that an m plus 1 is going to be in common in both those parentheses, which is a great thing. So I have 6 sum, that should be 2, sum of k squared must be equal to n times m plus 1 times 2n plus 1. And then I can solve this last equation by just dividing by 6. So therefore, the sum from k is equal to 1 to n of k squared must be equal to n times n plus 1 times 2n plus 1, all divided by 6. And this is the sum of squares relationship. So to sort of illustrate how this formula is executed, so for example, suppose I want to know 1 squared plus 2 squared plus 3 squared all the way up to, say, 7 squared. And I don't want to go that high. Let's go 5 squared. Now this you can probably do by hand, but I'm just going to illustrate this via the formula. So this is the sum from k is equal to 1 to 5 of k squared. So by this relationship, this is going to be equal to 5 times 5 plus 1 times 2 times 5 plus 1, all divided by 6. So we get 5 times 6 times 2 times 5 is 10 plus 1 is 11, all divided by 6. These 6's cancel directly, so we're just left with 5 times 11, which is going to be equal to 55. And that's how you can use the sum of squares relationship to quickly count the sum of squares of positive integers.